for electric machines. It was from 1960s, and they argued that, okay, we have this duty cycle and we are running this machine. And if I keep the duty cycle for a long time, the machine will heat up and reach its limit. But if I group the duty ratios with different duty percentages, I can maybe extend the temperature range a little bit and have a longer operation with more relaxed duty ratios. Actually, if you look at the literature, we can see that people have focused on this in 1920s, and one approach that was proposed in 1907, which was energy-based control, such that I squared T, for example, that was basically, okay, looking at the thermodynamics, E equals MC delta T. And if I want this machine to rise 80-degree temperature, right, this must be the energy that I must inject to this machine. And they actually show that I squared T is also the same for a given machine, not only the energy. And they use that approach, but that approach mostly applied to power transmission systems and power distribution for capability assessments, and they haven't really focused on that for electric machines. And in this work, I will use that approach a little bit, and the conventional exponential characteristic to figure out what the time ratings for electric machines are and how far can I push them. So if I am given a machine, suppose that somebody gave us a machine and said, run this machine to its physical limits, but I don't want you to burn it. What would we do? First of all, we would look at how would I do that? What kind of control approach should I follow? What kind of circuit would I use? What would I do to achieve that maximum output power from the machine? And the second thing, for how long can I operate at that point? I cannot operate that indefinitely. If a machine is rated 1 horsepower, its service factor is 1.15. I can operate at 1.15 horsepower indefinitely, but I cannot operate at 100 horsepower output power for indefinitely. And I want to find out for how long can I actually extract that much power from the machine. And if you look at this top figure, that actually I presented that 2 years ago in this seminar. And you can see I compared different control methods and how much extension, torque extension or power extension we can get from them. And it was for a machine that had 180 Newton meter breakdown torque, and we could get almost 3 times its breakdown torque capabilities using different vector control methodologies. And now I'm focusing on, actually in that presentation, I received a question that was from Pradeep Chenoy. He graduated last year, and he asked me, okay, so we have these curves that tells us how much we can extend the rating, but are those the physical limits for the machines? And back then I haven't really focused on thermal analysis, and I didn't have a definite answer. But now I can address this question, even though he's not on the line. So let's look at a very simple approach. Actually, on the left bottom, I have different temperature rise characteristics, and this one is the bottom. It's the rated current and how much it would rise my temperature, and this is in terms of percentage. So if I wait for a very long time, approximately 3 or 4 time constants, thermal time constants, this temperature will reach 100%, and it's exponential. And if I extend the rating a little bit, you can see I get these family of curves. And in principle, there is nothing that limits me from using, let's say, injecting I1 to the stator phases, letting it heat up at 100% temperature rise. I just switch back to I-rated and keep at this line 100% line. Okay? And that would lead to an extension in torque speed curve like this for a limited time. So, but how does the machine thermally respond to such a current? So, if we have a constant power excitation, this is the solid line here, the temperature rises, and it has 4 modes of heating. I put here different thermal characteristics too, for example, constant current and constant voltage characteristics, and I will not be focusing on them, but the difference is as windings heat up, their resistance increases. And if I have constant current excitation, the total amount of power lost under the same stated current will be increasing in time. So we actually have a rising relationship in temperature. And for a constant power operation, constant voltage operation, as the resistance goes up, the current goes down, the amount of power lost in the windings goes down, and that's why we have a smaller steady state temperature. Without loss of generality, let's look at the constant power loss. We have 4 modes as I described. The first mode is, I call it the sub-transient regime, which is associated to the time, to the characteristic where the winding, the conductor heats up, but it really doesn't transfer the heat to the ambient or anything surrounding it. It's just itself. I have a conductor, no heat transfer to the ambient initiated. It's just its own thermal capacity starts heating up. And in mode 2, I have this insulator around that. So the conductor heated up to some point where the heat started to disperse inside the insulator now, and it's slowly reaching the ambient. And that's what happens in mode 2. And in mode 3, it's a well-known exponential characteristic where people have modeled machines with RC circuits, right? And mode 4, I'm not really focusing on that right now because in constant power regime, it really doesn't happen or happens at really high if I wait long enough. But it is a temperature creep regime where this constant current excitation, you can see that more explicitly, the temperature just keeps rising. And it has a very high steady state value if I wait long enough. So in this paper, the experiments I run are for 5 horsepower 3-phase induction machine. And let's start the analysis. So in the transient regime, what happens? As I said, it's just a one parameter RC circuit. And if I look at the power balance, I have a stored energy inside the machine, inside the core or the windings. I have a power coming in, stator power. I have the power leaving out, maybe the shaft. And I have the power dissipated. That's the heat that's going into the ambient. And it doesn't have to be the power losses because the balance of this tells me how much power is being accumulated inside the machine as a thermal energy and how much is being sent out by convection. And if you follow these equations, we can actually come up with this exponential characteristic, as I was talking about. The total temperature thermal rise is an exponential characteristic, power loss over a convection term, or the heat transfer, well, thermal resistance to the ambient, let's say, plus some initial temperature term. And if we solve it for a fixed temperature, such as I want to run this, I want to find what P loss is, or for a given P loss, if I want my maximum temperature rise to be 100 degrees, 200 degrees, what should the time I should be waiting for, or when should I turn it off? And this expression, this logarithmic expression tells me, okay, I have this machine in this condition, the thermal resistance is this much, I'm running at 1 kilowatt power loss. Well, it tells me it's about in 10 minutes your machine will start smoking, so you can turn it off. But as I go to the shorter time scales, it really doesn't help me at all, and I'll show you why. And for different experimental characteristics you can see, this actually fits really well with the data, and actually some of the parameters is best obtained experimentally through curve fits because it's really a complicated process to find what the thermal resistance to ambient is. There are a lot of factors such as pressure, ambient temperature, surface temperature. It's dynamic, it's changing. Surface area, surface shape, length of the stator, everything affects this. So it's best obtained from a safe thermal run and calculate what the thermal resistance is and these parameters are, and the time constants. And for this machine, it's actually about 40 minutes. Okay, so if I shrink the time, which means I have this machine, its rated power loss is 400 watts, and I'm applying 500 watts, 600 watts, that characteristic is perfect. But if I want to say, okay, I want to run this machine 1 minute only, but I want to inject 15 kilowatts, 20 kilowatts, then that characteristic won't help me because it really doesn't capture the low-level dynamics that's going on while the windings are heating up. It's just a one-parameter model looking at the average machine and trying to guess what the temperature rise would be. But now, as I initially said, in mode 1, there is no heat transfer to ambient. So I can actually cancel out the convection term and just say that the thermal energy is being accumulated in the conductors. It's not even dispersing into the insulators. It's just getting accumulated. And that means we have a linear characteristic. It's just an integral of the power loss. And if I have constant power loss, that's what I assumed in this work, I get a linear relationship. And this MC is the heat capacity of the machine, conductors only. In the previous slide, we had, I don't think I put it here, but in this regime, you would look at the machine heat capacity, which is much larger than conductors. And in the subtransient, you would only look at the conductors because the conductor is heating up right now, not the machine. And we have fairly linear characteristic up to 6 per units of power. Okay, if we plot them, this is what we get. One of them tells me, okay, you are at 2 per unit. You should wait approximately 0.4 time constants. And the other one tells me, you should wait 3.29 time constants. Which one should I believe? Which one should I use? Because as you can see, as the overload factor goes up, these two characteristics converge. And if the overload is, if I'm not overloading it that much, it's just an exponential characteristic. So I would assume in this region, I would believe the solid line. And as I go further along, it's not really that clear from this figure because there are a lot of other factors affecting, but I will show you some experimental results where the transient regime would fool you, but the subtransient regime wouldn't. So what really happens in the transition? How would the heat disperse into the insulator? Well, we have, for a very large stator machine, this is just a stator slot. We have two conductors insulated around them and the wedge, and this is the air gap here. And for a, let's say, fairly small machine, this is the end winding structure. We have the conductors here in the shadow line, shadow area, and we have the insulator and just air outside. And for, let's say, low number of pole machines, let's say 2-pole machines, it's most likely to happen in the end windings, and a higher horsepower, higher pole numbers, it's more likely to happen inside the slots. So let's look at what happens. Okay, we have this heat being accumulated in these regions, conductor regions, during the subtransient. When the subtransient ends, the heat starts escaping that region and going into the insulator regions, right? And as it reaches insulator, a little bit convection starts. And this is the equation that captures the characteristic that's going on there. We have a correction factor here for convection, and if you look at how it happens, so it starts heating up, the insulator. This is the insulator range, right? So here the insulator inside surface that's touching the conductor is heating up, but the other side is still not experiencing anything. And as time goes on, this is how the insulator would heat up and how convection would start. Convection would only start if there is a temperature difference between the surface and the ambient. Otherwise, it wouldn't transfer heat. So here we have a small difference, right? And now the convection started. And we can see this is the characteristic, and this is the mode 2 region is where this happens. And that equation I presented actually fairly is a very good estimate for this. But in order to do this estimation, we need some parameters about the machine because, well, what I'm doing here can be replicated by really detailed finite element analysis. That would just tell me, okay, and I wouldn't need different equations, different analysis types, but that would mean I need a very accurate, very detailed machine model or machine information that the slot width is this much, the insulator material thermal conductivity precisely is this, and this is the insulator region thickness I'm using, which is really not that definite. You cannot know that. And there are a lot of other factors like impregnation in the windings to insulate them and not insulate them between each other and also have a better thermal conductivity to ambient. So all these factors comes together, and if I'm the user, if I'm the end user of this machine, there is no way I can know these parameters. The designer wouldn't tell me. I cannot sit down, cut a machine open, and measure everything perfectly. So up to this point, what I did is just use minimal geometric information about machine and try to estimate the time ratings. But here the subtransient regime actually requires me to know what the end winding parameters are, what the end winding surface area is, but these are still not that difficult to measure. If I have a machine, I can open it up without cutting it, destroying it, I can still measure these quantities and I can still estimate. So let's look at the estimations. As I predicted, over in this range, low overloads, modest overload operation, the transient regime is actually very well estimating my temperature rise and the time rating. But as you can see, as the overload increases, the estimation from the transient thermal regime is actually not accurate, and in fact, after this point, it's not meaningful anymore, because it tells me you have already reached that temperature. You cannot operate there anymore. But actually, it's not. And the subtransient regime is very inaccurate at the beginning, but after about 4.5 per unit overload, it provides very good estimates. And in between, I have the transition regime time rating estimation that tells me what my time rating should be and how long I should be operating there. So, but what is the ultimate capacity of this machine? What is the capability I can get maximum? Okay, so that depends on how much I can allow. How long do I have? 5 minutes? Okay. Okay, so that depends on how much I can let this machine heat up. That depends on insulation classes. I can use a machine with class H insulation, and that I can increase my energy density. I can make it smaller and everything. And if you look at this from an inverter operation, at fairly short times, maybe even sub-seconds, I can still see that the exponential characteristic holds. And there is a specific I square T constant for this machine for the ultimate temperature rise, which is 63,000 amp square seconds. Okay, and if I implement this for a real-time system like a hybrid electric vehicle with a very simple drive cycle like this, I can get two machines, one of them designed for 1.5 kilowatt rated power loss, and the other one is designed for 300 watt rated loss, but it's 5 times smaller. I can see that the first machine is actually rated for the peak demand of this drive cycle, and the second one is rated such that I can allow overloading, and you can still see that with class H insulation, I'm sorry, we can still be able to run this machine with maybe 1/5 the size of the original machine we have used in the first plot here, the solid line. So this is how this can actually affect our drive design. Well, what is going to supply that power to me? How can I get that much current? Because we have been talking about thousands of amps or hundreds of amps, and talking about maybe 10 seconds, 20 seconds, what is going to give me that power? Well, if you look at some of the common inverter topologies they use in traction applications, the right one is actually a hybrid Camry inverter, where we have the cold plate, the semiconductor is attached to the cold plate, and it's sandwiched. And on the left, we have a cold plate, and the actual semiconductor die without packaging is actually attached on the cold plate for cooling. Okay, how would this help me? So if you look at the time rating estimations for power switches, usually the manufacturers give us this curve, which is transient thermal impedance curve. We look at, okay, this is my duration of pulse, and I have only a single pulse. So looking at that number and multiplying with the power I'm actually losing on the switch, I can find how much the junction temperature will rise. But this is not really the dynamic approach I'm looking at, because this assumes certain waveform, and also it's not as meaningful as the lump parameter model, because these characteristics are usually generated for parallel RC lump models connected in series. So intermediate nodes really doesn't have any meaning for me. But if I had an actual lump parameter model with a series R and parallel C, then that would tell me junction temperature, KZ temperature, ambient temperature. I can model everything, but that would actually require me to know some geometric information about the semiconductor device. But a very similar approach that I presented about subtransient ratings was actually presented for semiconductor devices, And you can see if we have this die area, which is, assume it's very thin and just 2D, we can actually calculate how much the temperature will rise from using Green's functions. And for a very short time, we can go back to the subtransient regime that I derived, and the same physics still apply. The heat transfer didn't start, so we have the die heating up as it is, just accumulating. And this is how it has been determined since '93. Okay, let's look at how much, what this would mean for my derived system though. So I have two inverters. One of them is naturally cooled, the other one is forced cooled, water cooling. And the resistances to the ambient is 10 times on the natural cooled one. It has a very large package. The other one is just directly attached to the cold plate. And the heat capacity of this one is just the semiconductor heat capacity, and this one also has the heat capacity of the packaging. And suppose that if you do the analysis for the thermal resistances and everything, the steady state power for case one, I'm sorry, the continuous power rating I can achieve, power loss I can achieve is 16 watts, and the other case I have 160 watts. But also looking at the thermal capacity of the system, if I have 1 kilowatt losses in both of the switches, the left one will handle that for 160 milliseconds, the right one will not be able to handle more than 12 milliseconds. So this tells me, okay, I can make the packages smaller, I can make cooling much better, but does that really help me in terms of time ratings? It can expand the power density, how much I can push these semiconductor devices in steady state, but in time rating, I actually degraded its performance. And these are my conclusions. I had to be quick, I'm sorry. So do you have any questions so far? Yeah. Yeah.
So you pointed out that the package device had a higher thermal capacity.
Yes.
And then that suggests that it actually has a higher instantaneous power capability.
Yes.
But doesn't the cooling rails and so forth on the forced cooling system just become the package directly?
What we care about is just the heat capacity of the semiconductor, right? Because I want to know what the junction temperature is, and using this very short term, very high power density power loss characteristics that's derived, I should be looking only at the semiconductor.
But in the one, you have a junction between the semiconductor and some type of case material.
Yes.
And on the left, in case 2, you have a junction between the semiconductor and a copper cooling rail.
Okay.
So you have a junction either way, right?
Yes, but in the left case, we have extra packaging on top of that extra connection. Look at this. We have the die, we have the attaching material, we have the substrate, packaging, and then the cooling system comes. In the other case, we have only the die, substrate maybe, and then that's directly attached to the cold plate. So we have much more effective cooling, but far less volume that is actually heating up. That's the problem. If I increase the volume that's heating up, then I can send more energy because it's E equals MC delta T, and M is larger. In the second case, M is small. It's just one semiconductor die. It's just the semiconductor in it, no packaging, nothing. So that actually degrades the short-term performance. Any other questions? Okay, thank you very much.
Our next speaker is Ryan May. Ryan received his bachelor's from Milwaukee School of Engineering in 2011, and he's currently a master's student under Professor Pilawa, and he's planning on graduating in August. And his plan after graduation is to work at Texas Instruments in Dallas. Yeah.
Yep, that's
Yeah.
all I told him.
Yep, that's right.
Oh, yeah, the clicker. Okay. So as said, my name is Ryan May. I want to thank you for this opportunity to come and present at ECE 590 on the topic of my research, which is switch capacitor converters, particularly with applications of soft charging control. Hopefully I can figure this out. Okay. So let's actually take a step back from switch capacitor converters and look at switching power supplies in general. They're everywhere. Everything uses power these days. Everyone wants electronics in their devices, or they want electronic devices to do everything for them. But all these devices require power, and it typically needs to be converted before it can be used. So as a result, it's creating a growing design challenge, not only because we need electronics everywhere, but people are interested in efficiency and smaller form factors. So you can see here, here's an example of a typical inductive-based converter where we have transformer, inductor, and a large can capacitor, taking a large amount of volume for our converter. But while the common conception is that inductive converters are the only converters out there, it's true for a majority of the cases inductive converters can apply. So here we have an example of a buck converter. Otherwise, we've got boost, we've got buck boost, chook, other more elaborate designs that cover a majority of power electronic applications. However, there is another option, and those are capacitive converters that achieve these conversions without the use of a magnetic element for storage, but accomplish it all through capacitors. So we kind of have this dichotomy between inductive converters and capacitive converters. Inductive converters are known for a few things, very predominantly. Good output regulation and the fact that they're able to achieve arbitrary conversion ratios with high efficiency. However, inductors are inherently difficult to integrate and also have poor power density, and as a result, these passives are typically very large, and as a result of being large, can be also very expensive. Where on the other hand, we have switch capacitor converters, which, since they consist of solely switches and capacitors, those are two things IC designers have a whole lot of experience working with, and therefore are easy to integrate. And also, since capacitors are being used as the energy transfer elements, those are inherently more energy dense than inductors. We, however, do have some drawbacks. They're only efficient at a topology-determined conversion ratio. So this previous slide, we have a halfer, which is pretty much efficient only at converting Vin to 1/2 Vn at the Vout. And as a result of that, also, there is poor output regulation. So let's actually take a look at how these switch capacitor converters operate. You probably have an understanding of inductive converters where they switch between different phases or different configurations to accomplish these conversions. Switch capacitor converters are no different. So we have phase 1. In this case, we've got Vn connected in series with C1 and C output, allowing Vn to charge C1 and C output to 1/2 Vn to give us our half input voltage on the output. After some time, a period of time, it's switched to phase 2, where these capacitors are reconfigured using the switches to be in parallel with our output and discharged at a voltage of 1/2 Vn to this output, transferring more power. And this cycle continues ad nauseum until your battery goes dead. So, as you can imagine, since the only components in capacitor converters are switches and capacitors, understanding how these capacitors operate at a fundamental level is critical to making breakthroughs or even just having efficient designs that use switch capacitor converters. So if we look at a typical capacitor charging, let's say we just switched from phase 2 to phase 1. This capacitor here is discharged down to 4.5 volts, but we have an input voltage of 10 volts, which means that it's supposed to be up at 5. So the moment we reconfigure, we have this nice big current transient as this switch, or as the switch closes and the capacitor begins to charge back up to its full voltage. This current is set as a function of the switch resistance and the voltage disparity between Vn and Vc. This voltage disparity also is a key factor in our losses, which are substantial. With 1/2 C delta V squared, you want to keep this delta V as small as possible. So how that's accomplished typically is either through using large capacitors, which have a very small voltage ripple with a set amount of energy being transferred, or using high switching frequencies, which means there's a limited amount of energy being transferred per phase. Therefore, there's a limited voltage deviation from a set capacitor voltage. So how do we address this? I mean, that's one solution of just using bigger, more expensive parts, or switching faster, increasing our switching losses. There has to be another way. So one way that you can accomplish, or at least kind of help manage this delta V, instead of trying to get rid of it, we're looking at how we can control it. So if you place a regulating element in this loop, what it does is instead of having this delta V between Vn and Vc occur across the switch, causing power to be lost as thermal loss in the switch, it now occurs as Vreg across this regulating element. So this transfer does a few things. Probably the most important one is that instead of having this energy being lost in the resistor, it's now actually being consumed in this regulating element. Now you may think, well, that doesn't seem like a huge benefit because it's just being lost somewhere else. Well, in typical applications, I don't have a whole lot of ideal current sources I can just throw into my circuit, so we have an approximation of this current setting element in the form of a buck converter. This buck converter sets the charging current for this capacitive string and allows the delta V to occur across Vreg. So instead of there being losses, it's actually being converted into an energy transfer out through this buck converter. So it's energy transfer. However, since we're no longer interested in reducing this delta V, in fact, for our application in soft charging, we actually increase it to improve our power density, or the density of our converters. But this, as a result, creates a very large voltage ripple here on Vreg, which you'll be able to see in a little bit. Okay. So, as I talked before, we had a inductive capacitive dichotomy where you had benefits of one, cons of that same one, benefits of the other. With this melding, this hybrid configuration, you're able to focus on the positives of each particular converter style, at the same time having those positives mitigate the negatives of the other converter by having good output regulation because of our buck converter, and at the same time able to achieve relatively arbitrary conversion ratios. The capacitive stage is very easy to integrate and very high energy density, especially now that we're allowing for a large voltage ripple. So how do we actually accomplish this in reality with a switch capacitor converter? We have our halfer again, a typical switch capacitor schematic, and we replace this, our output load, with a buck converter, at which Vreg is now being represented by VSC, which has this increased ripple. So we have our switch capacitor stage serving as our transformation stage, our buck converter serving as our regulation stage and current setting stage. But this design, as a result of our switch capacitor stage no longer having a relatively set control frequency and allowing for this larger voltage ripple, it requires a more advanced control technique. So the past work in this area has been done by my advisor, Dr. Robert Palawa, where he looked at the series parallel configuration, which is a very intuitive application for soft charging, just based on how the capacitors interact with one another and with the load. And here we have the example of what that Vreg or that VSC voltage looks like. It has a substantial ripple. So that's what's been done. It's been shown to work, but the series parallel topology is not an ideal topology. It has a large number of components, and the voltage stresses on those components vary substantially. So my work has been in evaluating other topologies to see first what are their operational characteristics and to see if there's the potential that they can support the soft charging control scheme. So the result of my some of my research has been settling on the Dickson charge pump. This is seen as a very as a good converter topology for a multitude of reasons. So we're able to achieve a 4-to-1 conversion ratio in the switch cap stage with only 3 capacitors and a limited number of switches. And also the switch voltage stresses are minimal as a function of the output voltage instead of the input voltage. And then also this selection of the Dickson is also supported by some of the work by Michael Seaman and his work on the integration and operational characteristics of switch capacitor converters. So let's see if it's possible to use this traditional Dickson as a soft charge converter. So as we can see, actually I'll go back to this other slide. Just like in the Haffer case, each of these switches has a particular phase, which then corresponds with these loop configurations for the Dickson charge pump. In this case, we have loops that consist of typically 2 elements along with their output voltage, and these are set up in parallel. So one of the key things with this more advanced control for soft charging these switch capacitor converters is that the transitions between these phases are where problems can occur. So what we're going to do is we're going to look at the transition from phase 2 over to phase 1 and see if there's any issues with trying to implement soft charging in this 2-phase configuration. So if we look at this, so we have loop 1 of phase 1, where we're looking at our capacitor voltages. So at the end of phase 2, this capacitor has been charged with 1/2 Vn plus 1/2 delta V. And we go around, the second capacitor is charged to 1/4 Vn minus 1/2 delta V with V out in series. So what that does is it gives an expected voltage for Vn as 1/4 Vn plus delta V. Now when we look at our second loop, loop 2, we've got Vn in series with a capacitor that's charged to 1/4 Vn, which that is equal to our V out. The expectation for this loop is simply 1/4 Vn. So if you're tracking with me, we've got this loop comparison, and we see that one loop expects 1/4 Vn plus delta V, the other loop expects 1/4 Vn. So in a traditional or in typical switch capacitor control, where you're switching fast with large elements, this delta V is small enough that the negative influences of this disparity can be more or less neglected. However, in the case for soft charging, this delta V becomes very large to the point where it's on the order of volts instead of millivolts. So it creates a substantial problem. So what does this problem look like? So just looking at this phase transition again, and the characteristics of how these loops interact, each of the loops have a different expectation for V out, and as a result, we have these loop output voltage expectations. Loop 1 is expecting a slightly higher V out with the delta V there, and then loop 2 is expecting a slightly lower V out. So what happens is that these loops try to find an equilibrium. Now in both these cases, these loop currents are supposed to be positive, but in an attempt to find this equilibrium, we have loop 2 discharging a substantial amount of current back into our input source, only to later on in that phase start charging again. So even impulse current aside, the fact that we're just mindlessly cycling power from our input source into these capacitors contributes to losses. And as a result of this, our 2-phase Dickson really can't effectively support soft charging. So how do we find a way around this? Is the Dickson lost to us for soft charging? Thankfully, no. So what we're looking at here is the system desires to find equilibrium between our loops. So what if we arbitrarily allow these loops to converge to an equilibrium without these current transients? So if we isolate loop 2 and just let loop 1 discharge through right here until we get to a point where there's the intersection and the expectation for V out is the same, and then introduce loop 1 or loop 2, we're able to accomplish soft charging without these this nasty current cycling or current transients. resulting in these beautiful non-impulse-like current waveforms. What does this look like? So we have actually that new phase we call phase 1 prime, conveniently because it primes the system for phase 1. There's also an issue with the transition from phase 1 to phase 2 that requires a priming phase as well. So our final result is we have this 4-phase Dickson topology where we progress between these phases in this manner and then circle around. So how does this look? We understand kind of in this phase structure what the system looks like, but are there substantial changes to what it means in our physical design? Thankfully, no. This schematic here is the exact same one that you saw before. The only change that we have is that we have unique control structure of these 2 end switches. So we're able to accomplish this Dickson soft charging with just a little bit of control tweaking, independent control. So that's a huge plus. So now that we have these new phases, as you can see from the series parallel configuration, the phase transitions were determined by voltage switching thresholds. So how do we find these switching thresholds? Well, through the use of charge vector analysis, which is just kind of looking at how the charge is transferred between our elements, we're able to determine the relative spacing between these elements, and then there's an inherent kind of obligation for these those waveforms to be passing through the ideal conversion ratio, which results in a set of easily defined switching references. So if you look at this, here's our new characteristic waveform for our 4-phase Dickson converter. We start with phase 1 prime right there, starting here. It decays. We hit VREF 1, switches to phase 1, and then at the point it hits VREF 2, it switches into phase 3, or phase 2 prime, and then at reference 3, it switches into phase 2, and then it cycles back through. What do we have as our next steps? So I've been developing this on a theoretical platform, but have also been parallel developing a hardware application. So I've got this board on order, and all my parts are now in. It's capable of achieving selectable 8-to-1 or 10-to-1 conversion ratio with the maximum input voltage of about 100. A reasonably sized board. It's about 7 square inches. And it should be capable of processing about 200 watts at these conversion ratios. So conclusions, what I've been able to show you today is just kind of outline the soft charging concept and systematically develop it so that we can better understand what kind of work I'm up to. Kind of explain how I've been working on researching various converter topologies to see which ones can support this new soft charging control scheme. We walked you through the tests I did on the 2-phase Dickson and kind of the problems that I encountered. But that sadness was short-lived because we realized very quickly that there's a 4-phase solution that is accomplishable with very limited change. I'm really excited to see how it pans out in experimental results. Any questions? Yes.
Thank you. What's the characteristic of a regulation of your proposed hybrid converter? For example, if there is a step up or step down at the load current, how about your buck converter at the low side? How to control?
I mean, if there's a step increase or if there's an increase or a change in our load current, what that does is it affects the slope of the VSC. So, I mean, there's a predictable input current or input voltage to our buck converter as a result of the system loading. So we can track that and keep tight regulation.
Oh. As your mechanism, your buck converter at the low side is from giving a suitable current for your storing for your switching capacitor, right?
Mm-hmm. Yeah.
So your buck converter should give a suitable current for your switch capacitor, as well as give to give the sufficient current to the load. So,
right. So I mean the convenient thing is that this buck converter that we have in this series configuration kind of passes through the current that's expected at the load to our switch cap stage, and by that it sets the discharge current for our switch capacitor stage. So if we have a very low load current, then it passes through a very low current expectation to our switch capacitor stage, which then just causes frequency scaling in our switch capacitor switching, because it's entirely reference-based. So how much current is being consumed or being drawn out of our switch cap transformation stage, as long as, I mean, it's controlled by our buck converter. So it's assumed that it's just like a really noisy DC source to our buck converter, whereas the switch cap converter desperately needs the buck converter. The buck converter doesn't really need the switch cap converter in this case. Oh my. So many questions.
Okay. So with the Dickson topology, actually I haven't even done the hybrid, the advantages of the hybrid. So
Okay.
you have a buck converter already.
Correct.
And like some of the problems are the inductor, which is usually current rated. So your current, it looks like by stepping down the voltage initially, your current would actually be going up still. So
It would, yes, it'd be higher, but these, since I'm able to accomplish a 4 or 5 to 1 conversion ratio or step down in my switch cap stage, the voltage rating of my inductor can be a lot lower, as well as, since it's a lower voltage rated inductor, I can also switch that buck converter substantially faster. So the current, the expected, I guess, inductance of that inductor is lower due to lower incident voltage and higher switching frequencies.
I mean, it seems like the switching losses are way less because you apply this. Didn't you show a slide that said that the voltage rating of the switches in your Dickson topology were related to the output voltage instead of the input voltage?
Correct.
Yeah. So I mean, switching losses are really dependent on the voltage rating of those switches.
Yeah, I mean,
the RDS.
It's a function of RDS on. So if you have lower voltage rated switches, you typically have lower RDS on. Excuse me, and also just kind of based on our configuration, we're able to scale our capacitor and frequency of our switch cap stage substantially lower, on the order of tens of kilohertz instead of hundreds of kilohertz, which also lowers our switching losses. Did I actually end up answering your question, or did you just get kind of?
Following up on that, so the switches losses, the two components, right? The switch capacitor and then the buck converter, by implementing this hybrid topology, you are doing what to the switching losses and conduction losses?
Okay. Well, I mean, the conduction losses are entirely related to the physical configuration of our system. So, I mean, if you have switches and you're passing power through them, the conduction losses are the conduction losses. Since we're able to have our regulation stage be rated at lower voltages and also switching at higher frequency, we'll be able to have lower conduction losses there. When it comes to switching losses,
You have higher ones if you're going at a higher frequency.
for conduction losses?
For switching losses.
Oh, I said conduction, and then I was getting to switching.
Okay.
So, I mean, the switching losses, conveniently, since our elements are, as Josiah talked about, our voltage stress on our switching elements is lower because, I mean, in the case of the Dickson, it's a function of our output voltage, or VSC. If you were trying to do 100 down to 10 on a buck converter, you'd have to have switches that are rated for 100 volts instead of 20 volts. So I mean, you're able to have lower conduction losses there. For switching losses, I mean, we're still operating our buck converter at relatively high frequencies, but that's possible because we do have that low input voltage. So we're in about 250 kilohertz for our buck converter and about 10 kilohertz for our switch cap stage. So the improvement on switching losses on our switch cap stage is where we're getting a lot of our gains back on our switching losses. I should have made my presentation.
Hi, I just have a quick question about the particular implementation of. Can you go? Yeah, next. No, not go. I mean, go
to the end.
Yeah, to the end. We read it. Okay.
Right
so
here.
I just have a question. Like in your actual hardware implementation, how are you going to implement this like comparison between your actual voltage and the reference? Is it going to happen like in certain situations, like if you have really like heavy load and this transient is really fast, and it's going to, for example, meet the like the moment it hits the reference, it will kind of keep discharging to a certain like degree that it will still create a mismatch in voltage. So when you switch, it will still see the spike.
That is a good question. I mean, this spike is a function of this has one set of capacitors charging and the other set of capacitors discharging, and the flip is they change roles. So the charging capacitors become discharging capacitors, and that's what creates this kind of nonlinear voltage transition. Now, was your question kind of related to what happens if I have a substantially large current expectation at my load and I pass through one of these switching references?
Well, I think my question is basically how fast you can do this reference comparison. If it's slow, then
right.
if it keeps discharge, and again, like if you kind of hit the reference from this direction and you do not react fast enough, and it will, I mean, the relation between these two voltage will revert, and you will still have a mismatch
right.
in your voltage. So how is that going to affect?
So I mean, right here, I mean, this from here to here is about 10 kilohertz, and I have an external comparator, so I'm not chewing up microcontroller time trying to do analog digital converters. It's just waiting for an interrupt flag. So my microcontroller is operating at 8 megahertz, and this is